one more time with example 7 in the module 4 class notes. And if I never see another rational function graph again, I will die a happy man. I maybe shouldn't have recorded all of these videos back to back. And I hope you didn't watch all of the videos back to back, because your brain would probably be mush by now. But as mine is. But I can still work this rational function graph. So let's do it. We have this one last example of a rational function, and this one last time that I'll remind you, if you haven't watched example 0 in the module 4 class notes, please do so, so that you can familiarize yourself with the characteristics of and vocabulary surrounding these rational functions and their graphs. From there, let's take a look at this function, and small blessings. It's already factored for us. That's nice. We don't have to worry about factoring it, but we can jump straight to the domain then, where we find the x values that make the denominator 0, because the denominator can't be 0, so we get x can't be -2 and x can't be +4. And our domain in interval notation then is everything from -infinity to infinity, excluding -2 and excluding +4. On to intercepts, we plug in 0 for x to find the y-intercept. Do a little bit of math there, and we get +15 over -16, or -15/16, almost -1. Pardon me. So 0, -15/16 is my y-intercept. For the x-intercepts, we set the output to 0, set the y value to 0, and as we've done in previous examples, we set the numerator equal to 0 and get 3 x values. X equals 1, x equals -3, and x equals +5. So we have 3 x-intercepts. 1, 0, -3, 0, and 5, 0. Got lots of points to work with. And similarly, we can find us some asymptotes here. Vertical asymptotes, that's going to be where the denominator is equal to 0. We set x plus 2 equal to 0 and get x equals -2. The vertical line equation, x equals -2. And then from x minus 4, we get the vertical line equation, x equals +4. For the horizontal asymptote, we need to compare the degree of the numerator to the degree of the denominator. And to find the degree, we need to actually see what would happen if we multiplied all these factors out, but only the highest power of x terms. So x in the numerator, x times another x times another x is going to be x cubed. In the denominator, x squared will be x squared times another x will be x cubed. So I see I've got x cubed in the numerator and x cubed in the denominator. Then my numerator degree and my denominator degree are equal, and it being a 1x cubed and a 1x cubed in both the numerator and denominator, then 1 over 1, y equals 1 is my horizontal asymptote. Putting it all together, on my graph here, I've got this information with my x-intercepts, my y-intercept, my asymptotes, both vertical asymptotes and horizontal asymptote, and from here I could probably give a pretty decent sketch of the graph of the function, but not a bad idea to plot some additional points to make sure that we've got it. This time we've actually got a fair number of points. Let's just find a couple more. At x equals -1 and x equals +3. When x is -1, do all that fun math. Then we get y is 24 over -5. When x is +3, do a lot more fun math and get y is 24 over 25. So here, my y value is almost -5. And here my y value is almost 1. Plotting those points on the graph, I see that my graph is going to move in the appropriate directions, actually the directions that I had anticipated here, but my additional points helped me see that I was on the right track with what I was thinking. I don't know if it was what you were thinking, but additional points will always help as you kind of fill in the gaps here. Notice, so let me take this picture and give one last little look and discussion of what we're looking at here. To the left and to the right, there are no surprises, because from this x-intercept of -3, 0, we are opening a branch of the opening a branch of this curve of the rational function graph to approach the horizontal asymptote and approach the vertical asymptote. That's what we've seen on every example so far, and we see it again here. Similarly, from this x-intercept point at 5, 0 here, same idea. We are from that point approaching the horizontal asymptote, approaching the vertical asymptote, and we've got that branch of our rational function graph. It's a little more interesting in the middle, and two things that I want to point out. First, before the two things. First, we see this kind of more S-shaped curve in the middle of the graph, and that's perfectly fine. There's nothing wrong with that as a part of a rational function, and it's certainly also borne out by all of the points that we found. Both the intercept points and the extra points, the additional points that we found, are all just leading us to a picture of this kind of S-shaped curve. Let me note here then two things that I want to note. See here, that's not a hole in the graph, I'm just highlighting that portion of the graph. Here we have a portion of the graph that crosses the horizontal asymptote. Is that okay? Yes, there's nothing wrong with crossing the horizontal asymptote. The horizontal asymptote tells us the behavior of the graph, and I stated this all the way back in example 0. I'll say it again now. The horizontal asymptote tells us what's happening to the curve of the graph as x grows larger in either the positive direction or the negative direction. So you see how here we have a portion of the graph where the curve is approaching the horizontal asymptote. Same thing here. The horizontal asymptote is really only telling us what's happening on the ends of the function. In the middle of the function, the horizontal asymptote doesn't have information to give us, and that's okay. There's nothing wrong with that. So in the middle of the graph, it's perfectly acceptable for the curve to cross the horizontal asymptote. You will see the curve approach the horizontal asymptote toward the ends of the graph. Another thing I'd like to point out is the behavior here, where you see around this vertical asymptote at x equals -2, to both sides, to the left of that asymptote and to the right of that asymptote, as I've got it circled here, you see both curves, both branches of the curve are moving down in the same direction, where this asymptote here and here, the curves to the left and to the right are moving in opposite directions. So here, same direction to the left and to the right. Here, opposite directions. There's nothing wrong with that. Again, it's fine. But you can actually, the point that I wanted to make is you can actually see that behavior from the form of the function. This x equals -2 asymptote, where the behavior is the same, comes from this x plus 2 factor, where the factor is squared. The fact that that factor is squared, we call that a multiplicity of 2, means that we're going to get that behavior that's the same on both sides of the asymptote, versus the asymptote at x equals 4 here, where we're moving in opposite directions. That comes from this factor of x minus 4 that only occurs once. A multiplicity of 1 gives you that opposite direction, to the left and to the right, that behavior from the left and from the right of that vertical asymptote. They're moving in opposite directions. So again, we didn't need that information in order to give a good sketch of the graph, but it's a connection that we can make, and it can help us confirm, at the very least, it can help us confirm that our sketch is representing the correct behavior based on what we know about the form of the function. I'll have more to say about graphs of rational functions, and I'll be happy to take your questions on any of these examples or more examples as we record the live sessions for this week. So I hope you're able to attend those, check those out.